Okay, maybe it's time to start. So I'm Jari Nurmi. I will chair this second keynote talk session today, and let me quickly introduce the speaker, Alberto Bosio. He received a PhD in computer engineering from the Politecnico di Torino, Italy, in 2006, and then from 2007 to 2018, he was an associate professor at LIRMM, University of Montpellier in France. And now he's a full professor in the INL-ECL Centrale de Lyon, France. And as you will sure hear from his talk, his research interests are in approximate computing, but also in-memory computing, test and diagnosis of digital circuits and systems, and reliability. But without any further discussion, so I will just pass the floor to Alberto. So, prego.
Thanks, grazie Jari for the introduction. So can you see my presentation?
Yes.
Okay, so I now go to the full screen mode. So you're still supposed to see the presentation, right?
Yes. Perfect.
Okay, great. So I will start. Thanks also Jari for inviting me to give the keynote to NorCAS. It's a pleasure and an honor for me. So today my talk, as you already know, is about approximate computing. Let's say instead of focusing on the classical approach and context of usage of approximate computing, I will try to present some alternative usages of the approximate computing that are mainly related to the test and the reliability aspects of digital integrated circuits and systems. So first of all, let me start by the introduction. So I suppose that most of you know this chart. So this is, let's say, the problem that we have to face concerning the energy consumption of our computing systems. So this is actually the current, our current technology. So we have this increasing in consumption because we have an increasing number of digital devices connected and used by the population. And the point is that we are not really far from surpassing the world's energy production. So the point is that we have to reduce this energy consumption, and the goal is to go for this target, knowing that we have a physical limit of energy consumption per device. Now, one of the possibilities to move from the actual system to the target is to try to use approximate computing. And the basic philosophy that is behind approximation is the following. You can see from the picture that from one side you can have, let's say, a computing system that has to be as precise as possible, and to be able to provide this high precision computation quality, we have to pay a lot in terms of stress, where stress in this case can be considered as the amount of energy that you want to supply to obtain the computation. On the other side, we have another approach to do the computation. Here you can see from the comic that, let's say, among the overall set of operations, we may accept that some of them fails, some of them are not correct. And if we do that, we relax this stress, so we reduce the amount of stress. In other words, we relax the energy consumption requirements. And from the comics here, you still, you have the basic idea of the approximate computing, that is the following, that first of all, we can, let's say, accept this incorrect computation because we have few of wrong responses. Here, only the 3 red ones are not correct. So let's say we can consider the frequency of incorrectness is one of the key. And the second one is, let's say, the difference of the computed value from the wrong and the correct one is not so much. So the second key point is, let's say, the distance of the output responses from the approximate and the precise computing system. So giving that in mind, we can go further and let's say try to see what are the applications that can benefit from this way of computing. There is, let's say, the work from Chip in DAC shown that there is a class of applications that are considered as resilience. In other words, basically, they are able to produce acceptable outputs or good enough outputs, even if the hardware or the computation is affected by some errors or some noise. So I don't go into the details of all of these, let's say, class of computation. I just want to show you a couple of examples. And the first one is the one related to artificial intelligence and the convolutional neural network case. So here you can see, and I'm pretty sure that all of you can read this text, even if there are a lot of errors. But despite the noise that the text input has, we are able to extract the information. And basically here is an example where the application, and now in this case is the human brain, is able to, let's say, produce acceptable result because we can understand the text, even if the input is really noisy, or even if there are some errors during the computation, because our brain, for example, with the aging, will become the less efficient. But under a certain limit, we are still able to process the input data and to extract information. So this is clearly opened the door for a lot of possibilities to simplify, to optimize, for example, the convolutional neural networks. We can see some of them later on, in order to save basically energy and, for example, storage. So the amount of data that you have to store for implementing a convolutional neural network. Another example is still the classical one for approximate computing, is the limitation of the human being to, let's say, understand and again to process some images. Here, the example is the following. We have, let's say, an image that is processed by a median filter. Here, you have the, let's say, the correct output image, and on the left, you have a corrupted image where the corruption is done by injecting 10% of random noise. So we have the 10% of the pixels that are incorrect. So here you have a zoom, and you can see the difference between the two. A part of the zoom, you can still understand and perfectly recognize the image, even if it is corrupted. This again is similar to the example of before. Then on the bottom of the image, what you have is, let's say, what we can do in terms of approximation. So for example, we can, instead of executing the whole set of instructions of our filter, we can, let's say, intelligently select to execute only the 60% of the instructions. So we can reduce the 40% of execution time. And we still have, if you look at the zoom image, we still have a very good result, even if some pixel may appear to not be really correct. Okay. We can even go further and approximate even more by only executing 20% of instruction. And in this case, you see that some more pixels compared to this and to that are wrong, but still compared to this one, the output is really good. So in this sense, approximation, sorry, this is my computer, it is going crazy. In this sense, approximation can be really a possible solution to, for some application, to alleviate the energy cost. If you want to have a definition, Well, I don't provide you a formal definition. There are many papers in the literature that can do that. I want to show simply this chart where you can see basically the design space exploration. So where we can do and where we can go in the approximation design space. So if we consider this, let's say, as our reference design, and we consider on the x-axis, let's say, the accuracy, so the quality of the computation, and on the vertical one, the cost, or in terms of error, power, and performances, we can, for example, try to reduce or accept that the accuracy is lower compared to the reference design. But if we do that, we can increase the overhead reduction. So we reduce the cost, and where the cost, once again, can be error performance and or performances. And the interesting point is that we can proceed in this way until a certain point where we saturate. So it means that we cannot go further in the reduction of the cost unless we pay a huge cost in terms of accuracy reduction. So we cannot go in an infinite way in this sense. So the difficult point is to identify those, let's say, trade-off or design option for the approximate computing. Which techniques we can use? Well, there are a lot of them in the literature. So just let's say some of them will be used in this presentation. So the first one is the reduction of the precision. So basically, the idea is quite simple. Reduce the amount of bit to store variables and to store the data. So in this example, you have, let's say, the floating point 64-bit, the double precision, down to single 32 bits, down to 16-bit, the half precision that have been introduced by NVIDIA in the latest GPU cards. So this is an example where you can reduce your data. Reducing data means that you reduce memory footprint. Reducing memory footprint means that you can reduce the memory processor data transfer, so you have less energy to transfer data. And moreover, you have to compute with smaller data. That means you need smaller energy to perform the computation itself. Other examples are the loop perforation techniques. You can implement in different ways. So here there are just two examples of the loop perforation. So the idea is quite simple. So try to skip a certain amount of iterations into a loop in order to, once again, save execution time and clearly avoid to compute some part of your code, once again, for saving energy in the computation. Another way is to place at hardware level. So in this example, what you have is, let's say, a precise circuit. So you have a digital circuit that corresponds, in this case, to a 2-bit multiplier. You have the precise netlist, and here you have the approximated version of this netlist. And from this approximation, you can see that you have less gates, so you have an error reduction of almost 50%. Less error means, first of all, less, let's say, power consumption, because you have less gates that have to switch. And moreover, you have a shorter delay, meaning that you can increase the frequency of this circuit. But what about the impact of this approximation on the application? How we can quantify this impact? So to perform this, let's say, error analysis, we have to resort to what is called quality metrics. Once again, there are a lot of ways to compute this reduction of accuracy due to the approximation. And once again, instead of detailing each of these formula, I will directly move to one example that I think it will much more clear. And if we consider again our 2-bit multiplier, so the approximate circuit that we showed before, what we can do is to put in this table all the possible input combinations. So since it is a 2-bit multiplier, we have 4 input for A and 4 for B, meaning that we have 16 possible output values. And from this table, we can see that only one of the input combination provide a wrong result. So we can see that the error probability is 1/16 combinations. And the second point is that the distance of the faulty, or let's say the approximate value 7 is not really far from the good one, that is 9, and the worst case error is 2. So it is actually the absolute difference between the precise and the approximate version. So this is, let's say, an example where you can quantify the impact of your approximation by using those metrics. And then you can plug your approximate circuit into an application. And our example is use this 2-bit multiplier approximated into a JPEG encoding application. And you can see, or maybe you cannot, the difference between the two output images. We can use some, let's say, high-level metrics, for example, the signal noise ratio between the two images, or other image-related metrics like the structural similarity index, to quantify the difference between the two images. But let's say it really depends on the user constraints. And last point is that here the power reduction, thanks to the use of this approximate multiplier, was 40%. So we got an interesting reduction. Other kind of results. So those are results that coming from my research group. So we developed the design space exploration flow, and we ran it over a DCT algorithm. And again, what we proposed to apply was the inexact adders on the DCT. And once again, here you can see, let's say, the approximation images versus, let's say, the correct one. So it's quite hard to understand the differences. But we can, once again, try to put some numbers. And here we can see that we can, let's say, depending on the amount of error that we can accept, the area overhead is reduced. And once again, at a certain point, we cannot, let's say, we cannot go, because here 0.9% of error means that the image is quite, let's say, understandable. So we can consider that this is the good point. And again, for the the power consumption, sorry, here is shown in terms of switching activity of our digital circuits. This activity is lowered corresponding to the increasing of the error, so increasing the approximation degree. Another example is applying this design space exploration flow on a CNN. In this case is MobileNet V2. And here what we have is that we plot this, let's say, Pareto frontier, where we have on the axis the compression rate. So we try to maximize the compression. So we reduce the memory footprint by applying the weight sharing technique. So it is a technique for reducing the impact of the memory for a CNN. And on the y-axis, we have the error, that is the accuracy loss, the top one accuracy loss of our network. So let's say, what is the degradation, in the sense that how much we can go until the network is not able to classify anymore an input image. And once again, let's say, we have a good, let's say, compression rate from 5 to 6 x in terms of compression rate, when we have, let's say, a reasonable percentage of accuracy loss. While if we want to go further and reduce more the memory footprint, we have to pay a huge cost in terms of accuracy loss. But again, this is the trade-off to find between accuracy and overhead reduction for this specific application. Okay, I will now want to move to the test part. Once I provided, let's say, some basics of approximate computing, the techniques and some example of which application we can, let's say, which applications to benefit from approximate computing. And if we move to test, I want to, let's say, first of all, present the context, so where we are and where the test came into the picture. So basically here, if you consider this life cycle of a computing system, and for us it will be, let's say, the life cycle of an integrated circuit. Basically, what we have is we start from some requirements, we make our design, so we model the requirements, and then we go for the fabrication, for the manufacturing, where we have the final chip, and those chips are put into the final application for the in-field operation. Now, in this cycle, one of the points is that if we follow Murphy, we know that if anything can go wrong, it will. And this is exactly what happened in our integrated circuit life cycle. So we have problems, and let's say, just to summarize some example, we may have, let's say, our computer that freeze or cannot do anything, and we have to restart again our computer. And this is just an effect of problems that can appear in our integrated circuits. And the point is that those problems can appear everywhere and anytime. So starting from the design up to the in-field operation. So this is a huge portion of the integrated circuit life cycle, where we have to take care of this. Just to briefly go from the different steps and the different problems that we have to face, starting from the design phase, basically we may have errors during the design, but this is not, let's say, related to test, because those errors are mainly comparable to bugs that we can insert in our program. And the debug, in this case, is called the verification. We have to verify that the model of our digital circuit really implement the user requirements. So this is not test, and I will not spend much more time on this. And I go for talking about the manufacturing phase, where here we have to talk about the test. And the test basically is impacted because we have to face with the physical defects. What is a physical defect? Basically is something that is either missing, like in this picture where we have a missing connection here, we have a missing via defect that cannot connect basically a transistor to another component of the digital circuit. So we have something that is missing, or something that is present, and we don't want to have this. For example, we may have an unexpected connection between this point and that point. Okay, this is because manufacturing itself is not a perfect process. We can still have random defects affecting our integrated circuit. Now, the point is that what we have to do is understand if what we produced is defect-free or is affected by some defect. And basically, to do that, we have to resort to what is called the fault model. So we have a set of fault models that basically help us in modeling the behavior of the physical defect. And the classical examples of fault models are the following one. So we consider that a given net of our circuit is stacked at 0. So it means that it is always set to a logic state 0 or 1 because of a physical defect. For example, an unexpected connection to ground will lead us to have this stacked at 0. Okay. What is the test? Testing is the process after the manufacturing where we look for the presence of faults affecting our manufactured circuit. And just to give an example, if we consider this one as a circuit, we can, for example, apply these two input values, so 0 and X. X means that we can either apply 0 or 1. The result is that we have at the output the logical value 1 because of this circuit structure. And the interesting point is that if we apply this input pair of values to the two primary inputs, we can detect if the net A here is affected by a stacked 0, because if A is affected by a stacked 0, we have that the output will sweep from 1 to 0. So the red values here are the wrong values due because the fault affect our circuit. So this input pair is able to let us know if this circuit is affected by this specific fault. Clearly, we have many faults, many stacked faults, many fault models, and we have to identify the whole set of patterns, the whole set of input stimuli that can detect the presence of all these faults. Now, why approximation can be considered as an opportunity? Well, because we discussed before about the fact that we have applications that are intrinsically error resilient. So it means that we can have something that is not, we can rely on hardware that is not perfectly correct. So in other words, we can consider that faults are another way of approximating integrated circuits. And the point is that can we use this defective hardware? Because if we can do that, we can have, let's say, a cost reduction, because I don't have to test for all the possible faults affecting a given circuit, but the only point is that I have to test for what we will see are the critical faults. And if we can do that, we can increment also the yield, because I don't have to throw away all the faulty circuits, but some of them can be used for approximation, applications. Okay. So the tricky point is understand what happens if a fault appears into the hardware and is propagated to reach the software, and finally, what is the impact on the application outputs. So we already saw that we may have different, let's say, degree of faulty outputs. So once again, the image application. Here we have an application where no approximation is introduced and no fault affect the hardware. So let's say we have what is called the golden output. And then we have some outputs where faults affect the hardware, but let's say the output image is still understandable. I mean, it's still good. So we can classify those faults as benign faults, while some of them completely corrupt the image. So we cannot use hardware affected by those faults as an approximate circuit. So the tricky point is how to understand and to classify faults between benign and malignant, and then test only for the malignant ones. This is an example where what we target was as a circuit the ALU of the Palpino open source RISC-V microcontroller. Those are simply the statistics of this circuit, so it's, let's say, a small circuit. But on this circuit, even if it is, let's say, small, we still have 20,000 possible stacked faults. And to detect for all these 20,000 faults, we have to apply 450 test vectors. So 450 test stimuli to the circuit. And what we do is we want to classify those faults when we run this application. This is the DCT application of a JPEG encoder. Basically, what we can see is that those faults will be, let's say, further classified as benign and malignant faults. And the point is that the huge amount of faults belongs to the class of, let's say, the mask. So completely no effect. That is really interesting, and some of them lead those two cases where we have a degradation of the output image, but the degradation is higher than 30 dB of PSNR. So we fixed that the 30 dB is a threshold. So lower 30 dB, we consider that the image is not anymore usable. And even if you do this, let's say, we apply this threshold, we can see that only the 4% of faults leads to crashes and leads to these unusable images. That means what? That means that only 22 faults are, let's say, malignant faults, and it means that I have to test only for those 22 faults. That means that I can reduce the test cost of 95% because of the fact that I can use the faulty circuit as an approximate hardware for an approximate application. Then I have also some issues because once is saying, okay, I want to test a circuit, and if it is faulty, understand if I can still use this faulty circuit for approximate applications. Another is I build an approximate circuit, and then I have to test it. And I want to understand what the faults can, let's say, impact my approximate circuit. So coming back to our example of the 2-bit multiplier, here we still have our precise circuit. We have, let's say, another version of the approximation, where the approximation is even harder than the first one. And again, here you have the table where we can quantify the impact of this approximation. So here we have 4 wrong computation, and the worst case error is still 2, because the maximum difference is still 2. Now, we want to test for this, and we want to understand what are the impact of faults affecting these circuits. So here we have 2 examples where we have 1 fault here and 1 fault there. So we have 2 different tables, because we can, again, compute using the faulty circuit. And we can see that the 2 metrics that we use changes because of the fault. So in this case, the worst case error is not impacted, it's still equal to 2, but the error probability is higher. So in this second example, both of the 2 metrics are not valid anymore. So in other words, faults can impact our approximate circuit and make it even more approximate than the original design. So the point is that can we still use this circuit, this approximate circuit, but the question is, can we still use because it is faulty? And this is a problem, once again. And the point is that we have to understand clearly where we want to use this kind of faulty circuit and faulty approximate circuit, because we have to selectively test for specific faults. So just to give you some example where we can use these, we have, for example, this standard for the functional safety that is used for automotive, where there are what are called the safe fault application dependence. So faults that do not lead to a modification of the running application. So the tricky point is have these applications and perform the fault analysis and understand the malignant fault, and then generate ad hoc test vectors to detect only for these specific malignant fault. And once again, if we can do that, we have these, let's say, benefits that are, frankly speaking, the reduction of the, let's say, the increasing of the yield, so the reduction of the wasting wasting circuit, because we can still use faulty devices for a specific set of applications. Let's move to the last part of the talk, so the reliability. And coming back to our, let's say, life cycle, we move now to the in-field operation. And here, what we have to face are called failures. What does it mean? Basically, we have to consider that our electronic devices have to work in harsh environments. An example is the fact that we are, let's say, the more or the less exposed to cosmic rays. More or less depends, let's say, on the altitude, but even at ground level, we have some particles that can impact our electronic device. Here, the example is a neutron that impact a memory cell, and this impact generate a spike current that make the memory, the stored value, flipping from 1 to 0, or vice versa, from 0 to 1. Now, the problem is that as for the errors, as for the fault that we presented before, we have to understand the effect of these faults into our computing system. So moving from, let's say, the memory elements, so the RAM here in this example, up to the software and up to what is called system failure. So a difference of the application behavior compared to the fault-free application. Now, the point is that we have to, for a specific set of applications that are considered as the safety critical application, where we cannot, let's say, tolerate the fact that we have a faulty output of our application, we have to introduce some safety mechanism that has to reduce the potential risk or to tolerate the potential the problems that came from the potential risk. So this is an example where we have a certain level of random failure and you designed, let's say, an insufficient safety mechanism. You cannot be protected to this random failure. So clearly you have to know what are your, let's say, your problems and how to design a significant countermeasure to protect your system. And this let us coming back to our approximate computing field, because we can let's say reuse our original graph, but also considering this other quadrant of the chart, where what we want to do is exactly the opposite of approximation, because we want to increase, let's say, the accuracy of our computing system. And in this case, we talk about robustness. So we want that our electronic device can tolerate the presence of faults coming from the external environment. And to do that, we can basically pay some overhead, once again, in terms of area, power, and performance. And once again, we cannot do this operation forever, because at a certain point, even if we increase a lot, let's say, the overhead, we cannot increase anymore the accuracy, the robustness. So it seems that those two are completely, let's say, separated, and we cannot use approximation in this specific protected design space. But I will show you that we can do something interesting. And first of all, just to coming back and to make some example where we can apply this. So the opportunity here is the following. Once again, considering the application here is the object detection for an autonomous driving system. Clearly, we have to absolutely detect all these critical problems, because here the system cannot detect anymore the presence of the pedestrian. So here we really have a critical situation. But most of them are not critical, because here we still detect the pedestrian. Simply, let's say, we have a slightly translation of the object. So we have to be clearly intolerable and only detect for the critical issues in our system. What does it mean? It means that we can, for example, starting to do this, so we can apply approximation to our, let's say, fault tolerance mechanism and reduce a little bit the constraints, so reduce the overheads, moving in this sense our solutions. But if we do that, we reduce the cost, but we also reduce a little bit the accuracy. So in other words, we reduce a little bit the robustness. This example has been implemented, and you can see what is called approximate TMR. There are also papers describing the approximate TMR. I don't want to go into the details, but the point is that here what you have is three approximate replica of the same circuit and a voter. And the point is that in some cases it works. So if we have a fault affecting this module, the voter can detect it and tolerate it, and you have a correct output. But on the other way, you can have a problem, because here what you have is input X. For this input, this module provide a wrong value, and the fault affect this circuit, and at the end the voter cannot tolerate this fault, because you have 1, 2, 3 different outputs, and you have a reduction of the overall reliability of the system. Now, can we do better? We try to do better in this sense. We move radically the idea to apply approximation into the fault tolerance mechanism, and we want to do this. So we want to drastically reduce the cost without paying the accuracy. So the accuracy is still the same, but we drastically remove the cost of our robust implementation. How we can do that? We can do that by using, for example, what is called quadruple approximate modular redundancy. So here you have the difference. So instead of having the classical TMR, where we have 3 replicas of your system, of your electronic device here, you have 4 replicas, but the 4 replicas are approximation of our different approximation of our original system. The point is that what we want to do is make by design that for all the, let's say, all the possible inputs of our electronic, of our module, only 1 over the 4 replica is approximated, so that the other 3 can still be used as a precise answer and can be used by the final voter to tolerate the presence of an error. So this is the idea behind this QAMR. And how to implement it? Basically, once straightforward idea is the following. We can start by the, let's say, the precise circuit, and we compute 4 different replicas where we cut 1 of the output signal. And by cutting one output signal, we can simplify the circuit structure. And in this sense, we introduce approximation. So this first version only as we cut the S0 output, but we have a precise output for 1, 2, and 3. Here we have 1 that is cutted and so on. So at the end, we still have that 1, 1, 1. We still have 3 circuits over the 4 that provide a good result for a given output. So in this sense, the final voter is the same as the TMR, simply because we have always 3 replicas that are correct. And the tricky point is that understand if by doing that, the sum of the area of these 4 approximate replica is lower than triplicating 3 times the original circuit. Oops, sorry. Once again, my computer is crazy. Good. So we perform some results, and what we plot here are cases where what we obtain are circuits for which we cannot reduce the area by doing this QAMR fault tolerance mechanism, but we can reduce the timing. What does it mean? That we can reduce the critical path, and we can increase the operating frequency. For few circuits, we can reduce only the area without increasing the timing. For some of them, and not so much, fortunately, we don't have really a gain. We are really close to the original, even if we have a slightly higher cost. And the interesting point is that for many circuits, actually, we can gain in both. So we can reduce both the area overhead and also the timing. So we can reduce the performances overhead. So in this sense, we have an interesting set of circuits for which it is better to perform this QAMR fault tolerance mechanism compared to the TMR. Clearly, those are preliminary results, but we are currently investigating on a more extensive set of benchmarks to further validate this technique. So this leads to conclude my talk. So first of all, what I want to say is that approximate computing is still a hot topic, still because it's not, let's say, a young topic. It's more than 10 years that the community is working on this, but it's still, let's say, there are still open points to solve. What I presented is another way to use approximation for, let's say, for 2 application fields that are not usually, let's say, considered by approximation, that are the testing the reliability of integrated circuits. In terms of perspective, there are many points to solve, and I think that one of the most important is the automation. So automated tools and frameworks. The same space exploration is very complex because we have to add this extra, let's say, extra dimension that are the testing and the reliability into our frameworks. And also the fault classification is quite complex because it's still time consuming. We still have to run simulations to understand this, and it is really linked to the application and the workload applied to the application itself. So what happens if I change workload? Is still my fault classification still valid? So those are just two open points, but there are many others, and we can chat if you are interested in this particular field. I simply conclude by thanks many people because these works are let's say are collaborative works between many institutions, and thanks to you. And if you have any questions, I'm open.